Hello, my name is Brian Freno, and the title of my talk is Non-Intrusive Manufactured Solutions for Ablation. Ablative processes are an important factor in many problems of scientific and engineering interest. Because the removed material carries heat energy with it, ablative materials have been used in weapon applications, rocket nozzle coatings, and hypersonic reentry vehicles. Accurate prediction of the rate of mass and energy loss allows the designer to minimize the weight and cost of the heat shield. Furthermore, prediction of changes in the outer mold line is important in the context of hypersonic flight, where the aerodynamic forces and incident heat flux are intrinsically linked to the shape of the vehicle. Therefore, the simulation of ablating materials is a critical component of the design of future transportation and weapon systems. Verification and validation of such models are necessary to develop confidence in the credibility of the simulations. Validation assesses how well the underlying models represent the physical phenomena. Verification, on the other hand, assesses the accuracy of the numerical solutions. Solution verification estimates the numerical error for a particular solution, whereas code verification verifies the correctness of the numerical method implementation. Code verification has been demonstrated in many computational physics disciplines. For ablation, code verification techniques have been restricted to simple exact solutions. Here we present an approach for developing non-intrusive manufactured solutions. These enable the code to be more thoroughly tested. They do not require code modification. Instead of introducing a source term, we can manufacture the ablation parameter lookup tables. Now I will describe the equations we will be modeling. Our governing equation is the 1D energy equation due to heat conduction. We treat the material density as a constant, we express the specific internal energy as the integral of the specific heat capacity, and we model the heat flux through Fourier's law. With these modeling choices, we obtain the heat equation. To account for ablation, we note that the solid has an original thickness of L naught, which we express in the z-coordinate. Over time, the left side of the solid recedes by an amount s such that at a given instance in time, the thickness is the difference between the original thickness and the recession. The rate of the recession is modeled as the product of the char ablation rate B prime and the heat transfer coefficient divided by the material density at the ablating surface. The boundary conditions include a heat flux on the ablating surface that arises from the convective heat flux, as well as the energy lost from ablation. On the non-ablating surface, there is no flux. It is often convenient to use the Landau coordinate to normalize the position along the ablating material. However, in doing so, the time dependence of the material thickness introduces an advection term in the new frame. To discretize the equations, we use finite elements with a uniform mesh and piecewise linear basis functions. To integrate in time, we use backward Euler time integration. At each instance in time, our formulation yields the temperature at each node as well as the ablation rate. The arising equations are nonlinear, so we use Newton's method to solve them. Now I will discuss the verification techniques. On the left, we have the governing equations, and on the right, we have the discretized equations. R is the residual vector, U is the solution vector, and mu is the parameter vector. The discretization error is the difference between the discrete solution and the actual solution. The truncation error is the difference between the discrete residual and the actual residual. We can show that when the residual is linear, or linearized with respect to the solution, the residual of the discretization error is equal to the negative truncation error. For a pth order accurate discretization, the truncation and discretization errors can be modeled by a coefficient times h to the power p, where h is a relative characterization of the discretization size. We can compute the order of accuracy from two discretizations: a coarser discretization characterized by mesh size h, and a finer discretization that is q times as fine as the first. We can compute p by taking the logarithm of the ratio of errors divided by the logarithm of the ratio of the mesh sizes. However, in order to know the error, we need to know the solution. We can use exact solutions. These require a negligible implementation effort since they satisfy the original equations, but these cases are extremely limited and they span only a small subset of the application space. On the other hand, we can manufacture solutions the traditional way. These won't satisfy the original equations, so they require a source term. However, they can be manufactured to exercise features of interest. Alternatively, in this work, we propose manufacturing solutions by manufacturing the ablation parameters. This approach has similar favorable properties as the typical manufactured solution approach, and more importantly, there is negligible implementation effort because the manufactured parameters lead to an exact solution. Error norms are more useful than the actual errors for computing the order of accuracy. We can use the L1 norm, which gives us the average error in time and space, and we can use the L infinity norm, which gives us the maximum error. Now I will demonstrate the effectiveness of these approaches. For the first case, we consider constant material properties without recession, and our equation reduces to the constant coefficient heat equation. We introduce general boundary conditions with the intent of having them most closely resemble the ablation boundary conditions. The boundary condition for the ablating surface depends on temperature and time. To satisfy these boundary conditions, we decompose the solution into two components, one that is a simple parabola to solve the non-homogeneous contribution to the boundary conditions, and one that satisfies the homogeneous contribution. The latter is an infinite weighted sum of orthogonal basis functions. The zeroth basis function is unique in that it most accounts for the sign of the boundary condition due to ablation. With these basis functions, the coefficients can be obtained by solving a decoupled system of ordinary differential equations, and the initial condition can be projected onto the basis. As I alluded to earlier, we wanted our boundary conditions to be as general as possible to map them to the ablation boundary conditions. Therefore, by setting both equal and prescribing a general form for the wall enthalpy, we can see how the constants of this model equation map to the ablation parameters. Given these constraints, we can select arbitrary analytical functions that are smooth, continuously differentiable, and have generally non-zero derivatives for the pressure, wall enthalpy, heat transfer coefficient, and the recovery enthalpy. Here are how the temperature and heat flux at the ablating surface vary with respect to time for multiple thermal diffusivity values alpha. These different values change the relative weights between the spatial discretization error and the temporal discretization error. On this slide, we see how the temperature varies along the ablating material at multiple instances in time, also for multiple thermal diffusivity values. Finally, we perform a mesh convergence study using the L infinity norm on the left and the L1 norm on the right. We use 6 discretizations. Because the spatial discretization is expected to be second-order accurate and the temporal discretization is expected to be first-order accurate, we double the amount of elements and quadruple the amount of time steps for each subsequent discretization. Additionally, for the piecewise linear interpolation of the tabulated parameters, we double the amount of data for each discretization. Therefore, we expect these convergence rates for the temperature error norms to be second-order, which they are. Now we consider a more realistic case where the thermal conductivity and specific heat capacity vary with respect to temperature. We employ a Cole-Hopf transformation which introduces a new variable theta such that the heat equation can be expressed as a constant coefficient heat equation. The general solution is a sum of sinusoidal functions weighted by time-varying coefficients. However, because the arguments of the sinusoidal functions vary in time, separation of variables is not possible this time. Therefore, we reduce the solution by enforcing the boundary condition on the non-ablating surface. Next, we express the boundary condition on the ablating surface in terms of the theta variable and write b of t in terms of the preceding terms. As with the previous case, we can now map the ablation boundary condition, in this case, to the actual ablation boundary condition. We can most generally express the wall enthalpy in terms of two pressure-dependent functions, and the function from this case is boundary condition. We can then express the remaining boundary condition terms in terms of the ablation data and recession rate. As a numerical example, we specify the temperature dependence of the thermal conductivity and specific heat capacity to be exponential. Consequently, theta is related to the temperature proportionally to this dependence. For convenience, we take our general solution from before, truncate the non-zero index terms, and opt for the hyperbolic sinusoidal function. This provides us with a simple expression for theta, which can be mapped back to the temperature. And for additional convenience, we have the temperature dependence of the boundary condition be exponential. We then determine how the remaining boundary condition terms are related to the ablation data and recession rate, and we manufacture the recession and pressure. Now we can determine the functions for the remaining ablation data and choose our constants. Given our choices, here are how the ablating surface temperature, heat flux, and recession vary with time for multiple thermal diffusivity values. We have deliberately induced a large amount of recession to fully exercise the mesh deformation implications. On this slide, we see how the temperature varies along the ablating material at multiple instances in time, also for multiple thermal diffusivity values. Once again, we perform a mesh convergence study using the L infinity norm on the left and the L1 norm on the right. We expect these convergence rates for the temperature error norms to be second order, which they are. If we look at the convergence rates for the recession error norms, they too are second order. To summarize, in this work, we manufactured solutions by manufacturing the problem parameters instead of introducing a forcing vector. This approach enabled us to avoid modifying the code, and we saw that the code achieved the expected order of accuracy. Thank you for listening to my talk.